All right, so welcome everybody. So tonight we're going to cover two more DeepSeek v3 DeepSeek topics. First will be multi-token prediction, and then the mixture of experts. And I think Ted's going to provide the specifics, kind of particulars for DeepSeek. With that, let me go ahead and. Okay, Ted, I should have given myself a presentation rights before I gave you the host. Okay. Oh, you know what? I did not do, let me stop and do that. I didn't do the optimization thing.
Yeah, your screen is a little small there too.
Okay. I don't know why it's not saying. Okay, you'll have to tell me if the video works when we get to that. There's one. How's that? Can you see that okay?
Looks good.
Okay. All right, so this is the multi-token prediction. So the papers that I went through, just briefly, there'll be one section we'll go through on DeepSeek. It's actually really is, it's like less than a page. But then it references a couple papers. One was this better and faster language models via multi-token prediction. So this is kind of the reference paper for multi-token prediction. And then there was another one. So in talking about multi-token prediction, I think one of the things that comes up is inference optimizations that you can do. And to do that, we have to talk about speculative decoding. And so I had a little section on speculative decoding. This was the original speculative decoding paper, apparently. So those are there. Let me, where's my share button? I'm going to post this. I'll drop that on the chat if anybody wants it, and then we'll put it in later on. We'll add it to the Slack channel. Okay, very good. So in the paper, was there a question, Jerry?
Oh, no. Okay. I just clicked the thing and hang on a sec. I gotta flip my screen back here.
Okay, so I'll go ahead and continue then. So this is the, let me see if I can put this out of the way in case that was blocking it. This is the graphics, the image that kind of describes the multi-token prediction. So the concept here is that in general, when you're dealing with autoregressive language models in generation time, when you're doing inference, you essentially will take a context, which is a sequence of tokens, and you'll predict a distribution of the next token in that sequence, only the next token. That's the way they work. But in this multi-token prediction, you're going to predict not only the next one, but n additional tokens in the sequence. So this diagram is I found to be a little misleading, but basically think of it here as the first one. This is a sequence going into the transformer and a sequence coming out. So in essence, each one of these tokens goes through this model in a forward pass through the model. So T1 would go through this model in a forward pass and predict a distribution over T2. And T2 would go through the model, forward pass, produce distribution over T3, et cetera. And in this case, let's assume that we're like in a training mode, so T1 through 6 is known. We're taking in 4 tokens and predicting 4 tokens. Those are, for each position, we are predicting the next token, just the next token. Comes in, gets embedded, goes through multiple layers of these transformer blocks, an output projection head into the token space, and then they run the cross entropy loss. That's the training signal for the prediction of the actual token. So these would be the target tokens, which is the same as the next input token. That's all standard. Any questions on that? I think we've been over that a few times, so. Okay, so what they do here, though, is they then take this top level. These are I believe this is still in the embedding space. They take that top embedding space before the projection into the token space, and they run that into another layer, let me call it, another model. And that model takes a combination of this top level and then the embedding of the next character. And it will use that. So it'll take, here we embedded and predicted T2. Here we take that and we also embed the actual T2. We do a projection, and I didn't find any particulars. I didn't look for any particulars on what this transformer block is like. I'm guessing it's probably similar to these transformer blocks. Then they run it out through the projection and get back into token space. They do note that these embeddings, top and bottom, embedding layer and the output head are all shared weights. So those are all identical. This transformer block is not shared weights with these transformer blocks. It's unique. And likewise with the projection. And I think RMS norm has some tunable parameters as well. Those would be all separate. So adding this, embedding this hidden space to this one, concatenate it and predict the next token. So T1, 1, and 2 is used to predict T3. And then over here, they do the same thing, just repeat it, and they can repeat it some number of times. So T1, 2, and 3 are used to predict T4. So that is the basic concept. They referenced it as sequential. So they're doing projection here, and then sequentially they go through here using the output of this. The first one, module 1, will do its projection, and module 2 uses the output of module 1. So it's that sequential, they say, to maintain causal relationship. Any questions on that part? Pretty straightforward, really.
So Roger, I don't know what you're going to cover in your other slides, but like this is like a very non-obvious design to me.
Yeah.
So I'll reserve my comments till after you cover whatever else you're going to cover. But like that other paper that you referenced, the original multi-token prediction, it had a very simple design,
Yeah.
Boom.
Yeah. So why don't we do that and come back to this? Because I had the same question. Yeah. It's like I can understand what they did, but I didn't read any references to why they did this, what they were trying to achieve, other than that maintaining causal relationship between these nth token prediction. Okay. The other part to look at is just what's the loss function they're using for training this. And they're basically just doing a cross entropy between the predicted distribution and the actual token in the n+1 location. And then they add, so lambda over D. So D means they're averaging it for all of those predictions. I think this is just the nth. Does this start at 2 plus k, I equals 2 plus k to 1. I think that this is in addition to the primary cross entropy on the main transformer block. So they're averaging that n and scaling in with this lambda. How much weight do I want to assign to these nth token predictions? And so the loss function, then you're going to have these up here. Yeah, see, they call this main, and this is MTP1, L2 MTP. So the loss function, the gradient's going to flow back down through this, through here, and then back down in to the main transformer. And that's important because we'll see a little bit later that the primary objective they were trying to do is affect how this model is trained, influence how the model is trained, the quality of the model that's trained. These are, in their view, kind of incidental to getting to that, achieving that goal.
Roger, can you go back to that just for a sec?
That one?
Yeah.
Or that one?
That one.
Yep.
So I'm just looking at the, like in the center one and the right one, it has next 2 in real tiny type and next 3.
Okay.
Is that just, are those just names for them?
So this is the next token prediction. So 1 predicts 2.
Right.
Here,
2 predicts 3?
Yeah, 2 predicts
Okay.
3. Yeah, and 3
And 3
predicts 4.
predicts 4.
Well, I shouldn't say 3 only because it's using 1, 2, and
Right.
3.
Yeah,
Yeah.
that was kind of where my question was going. Is it's looking back and using all the previous ones too, right?
Yeah. I
Okay.
mean, you might want to use notation, next to 1 or something. Yeah,
Yeah,
it's using both 2 and some embedding from 1. And
to figure out.
somehow
Yeah.
this is
Okay.
influencing this embedding during training.
Gotcha. Gotcha. Interesting.
They didn't really go into why. So one of the things that I picked up, and Ted, you had pointed this out one of the other times when we were talking about it, is they do it for their objective is training a better model. It's not for inference. So as we're going to see, speculative decoding is something that can improve inference performance. I was kind of shocked given the emphasis that they've had on kind of efficiency, et cetera, that they weren't taking advantage of this. They did mention that additionally, we can also repurpose these MTPs for speculative decoding to further improve generation latency. So yeah, they can do it, but it doesn't sound like they were initially. They might by now, maybe they are. I don't know, but I thought this was interesting that their goal was just the model. Okay, and then here, this is the one justification that I saw is that also for each MTP model, its output head is shared with the main model. Our principle for maintaining the causal chain of prediction is similar to that. I did not go read this one, but the other one was primarily for speculative decoding, whereas they're using it just for NTP to improve training. So yeah, that was one thing that caught my eye is they weren't using it specifically for training. Any questions on that?
Yeah, Roger, if you go back to slide 3,
Yeah.
So at a time, how many are they predicting and how does the flow work after they have that multi-token prediction?
Well, there is a flow that's associated with speculative decoding that we'll go through if we have time.
I mean for the training time.
Well, all they're going to do is feed in. This will be the model, and they will feed in, a sequence T1 through 4 with a label or a target token of T2 through 5 here. And they'll just feed in a different, shifted set of tokens in, shifted set of tokens out. And they'll do that for however many MTP modules they use. I don't recall reading how many they actually trained with. Ted, did you notice that?
I don't know if they said it.
Okay.
I think it was more than like here they show 2 and 3, right? I think it was more than that, but it was not a ginormous number. It was like you could count on your fingers, I think.
Yeah.
So another question that I have is, go ahead, Roger.
Yeah, so they're basically then this just going to be standard training. They're going to feed the input sequence in. They're going to get the outputs. They'll measure the cross entropy on the prediction of each of the heads, and then the gradient's just going to flow back through this. So there's no special steps, I don't think.
So during training, of course, we already know the next tokens and all that, so we can parallelize the training for each token prediction irrespective. So what is the benefit of this if they're not using it during inference?
The benefit seems to be that it trains faster and gets a better prediction out of this. Somehow the embedding starts to include some sort of looking forward type of thing. There's a little bit of talk of that when we get into the next paper. They talk a little bit about why they think it worked, but the DeepSeek did not talk about that.
So let me rephrase the question. We are adding more compute, and yes, I see the point that it may help with the forward-looking, look ahead, or something like that. But it is more flops for training because your first column, a regular autoregressive model training, will have all the tokens and train everything anyhow, right?
Yeah.
So now we are adding more compute, and the objective is that this extra compute in columns 2, 3, or whatever number it is to help with the maybe look ahead of the output head, or because that's the only thing that's getting trained.
Yeah, it provides, it's more compute during training time. It's not test time compute. And it doesn't add more parameters because they drop these when they're doing inference. But somehow it's providing a gradient back through this little branch, back into these transformers so that they are they're doing a better job of predicting. So in the next paper that we'll talk about, which I might shift to because it's 6:52, this was the paper that they referenced, the Fabian, the Better and Faster paper. And this is where apparently they introduced the multi-token prediction. In this model, again, a little bit confusing the way they show up, but this would be 4 tokens. There's a forward pass through the model, so this isn't anything special. It's just four forward passes through the model. And they actually then had a different projection head for each of the predictions. So the standard one takes in whatever this embedding is and predicts the second token. The second head predicts not the second token, but the third token, et cetera, through however many heads. I think they went up to 8 heads in some cases. And so this was a different model, a different way they did it. And this is, to Ted's point, Ted, you say this is more natural, I guess, to you than the other.
Well, it's more obvious what you're doing, and it's simpler. All you're adding is a single linear layer for each additional token that you're predicting. Whereas here they're adding an entire transformer block for every additional token you're predicting. So, which, to Dave's point about compute though, right? If on the left you have 60 layers, each additional token prediction, it's more than just a linear layer, but it's still only 1/60th as much compute. So you're only adding 1.5% to your compute.
Yeah. And to me, this one, I'll do counterpoint. This one actually, to me, made a little bit more sense because in this case, when I think about predicting it in a sequence, it's easier to predict the third token if I know what the first and second are. And as opposed to this model, the Better and Faster model, where it's kind of like you predict them all at once, right? This one kind of allows you to narrow in on, okay, so what did layer 2 pick or token n+2 pick, and I'll base my n+3 based on that. So that's just counterpoint to that. I don't know what the motivation was.
It's a larger receptive field, you could say.
Kind of
forces the training to be able to be useful to the longer token sequence. In other words, the first stage has to be as useful as it can be to the subsequent stages.
Right.
So it improves its representation on a token span that's larger than 4. So it's like effectively a larger receptive field for the overall training.
This one, though, also kind of has the same effect in terms of the field. This one also has the advantage of these can all be done in parallel, whereas the DeepSeek, these have to be done sequentially. So from a latency perspective, it increases the latency of the model. Did you want to have any more discussion, Ted, on that?
No, for the sake of time, I mean, they're both doing like what Julius said, and I like that from the idea that if you commit to sort of a sentence or a phrase, you know what I mean? Sometimes the first word kind of commits you, in that direction. Right. And so I would rather, I think that calculating your loss over a wider receptive field, as Julius said, like over the course of the next sentence or the next clause, is more semantically, in my mind, can be more semantically meaningful, whereas just over the next one word can often be very short-sighted, right?
Yeah.
You know what I mean?
Yep.
Yeah.
That kind of leads in here to this. So these guys did a little bit of kind of thought analysis on it. One thing I noted that I just wanted to point out is it actually did worse on smaller models and did better on bigger models. So next token prediction may be something that's only useful on larger models. I don't know if DeepSeek had the similar kind of.
Wait, Roger. Which one would do worse? Which one are we talking about?
These are like 0.3 down here. The
No, no, no,
performance.
but which process? The DeepSeek one or the other
Well,
one that you showed?
this we're talking about this paper.
That one. Okay. All right.
Yeah, I don't know that DeepSeek did this analysis. I'm just saying it was interesting that multi-token prediction, perhaps done this way, perhaps DeepSeek is a different result, but the way they did it, it only seems to work for larger models. Although, as I look at it here, now I'm realizing what they call a larger model is 13B. So, maybe it's just something, But anyhow, the small ones, it didn't help. So that was kind of interesting. This is their comment. They did a little reflection, kind of why is this working? And what they were claiming, their insight is that it mitigates the distributional discrepancy between training time and inference time. So the idea is that, where is it?
Sorry, Roger, this Y is for the previous paper, not DeepSeek, right? I guess.
What's that?
That slide was for the previous paper, not DeepSeek, right?
This is for the seminal paper on multi-token prediction. Yeah. And I was going through here because I'm trying to remember, maybe I didn't copy and paste it in here, but they're basically saying when you're doing training, you got at each point you're kind of predicting just the next token, and so there's a certain constraint or behavior associated with that. Whereas when you're doing inference time, it has kind of unconstrained. So, what happens in the third token depends on what you did in the second token. And you can kind of get errors that accumulate during that. And they were causing that or calling that out as what they thought bringing that information back into the training was helping the model be better at managing that error during inference time. This was something that they said here and also came up in the speculative decoding is interesting. Not all token decisions are equally important for generating useful text from language. Some are more important. And what they were thinking this would do is this would help it make good choices at those important ones. And this apparently, if you do an analysis of it, it increases kind of the weight, the gradient flow back when you have those multiple tokens if they're strongly correlated. Here it is. Yeah, here we go. Language models are typically trained by teacher forcing. That basically means supervised learning, where the model receives the ground truth for each future token during training. However, during test time generation, it's unguided and autoaggressive, whereby errors accumulate. And they're arguing that teacher forcing encourages the model to focus on predicting the short term, but potentially ignoring some of the long-term dependencies. That was their insight. This was their results.
And Roger, in the older paper, during inference, they still continued to predict only one. They did not do any kind of speculative decoding kind of prediction in that previous paper. Is that right?
Okay, so it depends which. So this is the one on multi-token prediction. Yeah, they actually do some, but their emphasis was on quality of the model, not on speed.
Right, but during inferencing, how did they?
They were just doing single token. That's what I'm saying. It's just to get a better model. It's not for speeding up training. Speculative decoding is different. They're focused on performance. They do it a different way, but it turns out this multi-token prediction is very compatible with speculative decoding. And we can see that, except that I've got a hard stop. Yeah, this was the Better and Faster Language Models paper. So they did say that as an additional benefit, models trained with 4-token predictions are up to 3 times faster at inference. But that's not what they were trying to achieve. What they were trying to achieve was better performance here, which when you look at it, isn't hugely better. It's like a 10% gain or something like that on some of these. But anyhow, so why don't I stop there? And speculative decoding, we could probably work in a session later on that. Does that make sense? It's not directly DeepSeek. Does that make sense? Ted?
That sounds fair. Yeah, I mean, if by some miracle we have time at the end today, we can squeeze it in. Otherwise, it can fit anywhere. It doesn't have to go with DeepSeek. I will say one last comment in terms of this idea about like teacher forcing next token versus like looking farther out. I think that's one of the reasons why you see for things like alignment. So like the training the LLM's tone and anything around like you know, gender bias, that kind of a thing. You notice we've been using things like RLHF. We are not using supervised fine tuning. And that's because something like tone, I think, is hard to measure at a one token
Right.
level,
Right.
right?
Mm.
You can use the word no a lot and not be negative in tone. And
Yeah.
you can use the word yes a lot and still be very negative in tone.
Yeah.
You know,
Yeah.
yes, you're an idiot or whatever. You know what I mean? Like, so,
Yeah.
so I do feel like that's consistent. That conventional wisdom, right? Since we can't get things that like tone that emerge over longer sequences trained with supervised tuning, maybe in general supervised training only looking at one next token is a little bit short-sighted. So I kind of agree
Right.
with the author's speculation. It's not proof, it's just speculation.
So it's the auto-regressive nature of it, right? Single token prediction, basically. You're just looking at
No,
that next token, and no isn't negative. It's independent.
you just don't have enough information to know
Yeah.
whether or not it's negative.
I
As like a
thought
very simple example.
so. I didn't know if this paper took it from speculative decoding or vice versa. They both had this same concept, which I think is an interesting one to keep in mind, and that is that not all tokens are the same importance. Sometimes, it's very easy to know what the next few tokens are, but there's inflection points. So treating them differently, I thought was pretty cool concept.
Yeah.
So,
Cool. Thanks, Roger.
Mhm.
All right, look at us trying to manage time.
That's unlike us.
Unbelievable.
Yeah, very unlike us. All right. So let me move this. All right, so hopefully nothing's blocking your screen. So last few weeks we've been talking about some different components that are in DeepSeek, in particular V3, R1. Uh, um, and as we've seen, most of these things were not invented by DeepSeek. They tuned them to make them work better, for sure, and they threw a lot of them into the same model. So these are all like good things. So one of the last ones we wanted to talk about is mixture of experts, which again definitely was not invented by DeepSeek. So so what is mixture of experts? So high level, it's a neural network architecture design where the data flows through parts, subcomponents of your neural network in a variable fashion. Okay. You can debate like who, quote unquote, invented mixture of experts. There have been people who've proposed different ideas for that are akin to mixture of experts for many years, going back more than 10 years. Okay. We're going to talk about a particular one, which is sparse mixture of experts that people use in large language models. And these are used in the MLP layers inside your transformer. Okay. In terms of the name mixture of experts, one early design that was discussed is having full models. Okay. So you could have Llama 3 and you'd have my really good at math Llama 3, my really good at French Llama 3, and my really good at, say, biology Llama 3. And you can imagine that the word expert there is very intuitive, okay, in terms of like, this question is about geometry. Let me give it to the math Llama 3. Of course, you need to figure out what the topic of the question is and choose your model, right?
That I assume that I assume is just based on the training, the data set they use for training.
Yeah, and they don't even have to be llama threes. It could just be like, oh, when I
Whatever.
do have a coding question, I use whatever, O1, and when I have a poetry question, I use Gemini or something,
Right. Right.
right?
So something
Well,
like mixture of LLMs. Sorry to interject.
Yeah.
well, it's just an ensemble technique, but I
Okay.
bring this up just because the term expert kind of makes more intuitive sense there. Okay. What we're going to see is that what these quote unquote experts are doing is far more fine grained. And so if you have a notion that like one expert is good at biology and one's good at French, that is not what's happening here. Okay. So we'll get into what the technique is and the details. And what we'll see is that the advantage of mixture of experts is that it gives us more expressive power for the same number of parameters. It is less compute during inference than fully dense architectures with the same number of parameters. And something that I hadn't really seen people talk about too much until the DeepSeek v3 paper is that they say that their mixture of experts model actually trained faster. They got a better model after, 100 billion tokens than you would have in a non-mixture of experts model after 100 billion tokens. So I've seen that a couple other places, but I didn't realize that until I started prepping for this discussion.
Hey, Ted.
Yeah.
Could you give me some intuition on that the first bullet, greater expressive power?
Yeah. So basically the idea is if you have 20 parameters and you just simply pass everything through all 20 of those parameters, then basically it's like your expressive power is, if you think about it, if you just sum those 20 things, so then each one of them is like a line, right? And so because you've got a ReLU, it's not actually a line, it's a segment because the ReLU can chop off half of it, right? Mm-hmm. And so effectively you've got like 20 line segments that you can sum together.
Okay.
If instead of ranging them just as 20, you insert a little something that says, I'm going to use 2 of them and variable weight the 2 of them, and do different mixtures of those, then now effectively you've got many more different possibilities you can output from this. Technically speaking, you have more parameters because you've got parameters for the choosing of which 2 out of the 20 to use, but assuming that's a very tiny number of parameters, that effectively for the same number of parameters, now you have more possible outputs. Because before, you didn't have the option to turn off some of the 20. They were always on.
Okay.
So now by basically being able to turn them on and off, you've added more expressivity to your outputs.
Okay.
And I think that is potentially the explanation for the faster training, is that on a level for a very, very small change in parameter count, you actually have more expressivity. So one disadvantage of mixture of experts is that you need more memory during inference than the dense architecture that uses the bare minimum. So we'll get into the details, but basically mixture of experts is good if you're DeepSeek or your OpenAI and you're expecting thousands, millions of users and your servers are spreading the load across many different users and balancing the load. If you were just running a mixture of experts model on your one personal computer, then you might not be as crazy happy about that model because it's going to use a whole lot of GPU memory, and then after it's loaded all of these weights into memory, it's actually going to not use very many.
So the extra memory is used for parameters, right?
Yeah.
So the idea is that you have more parameters, but you have the same number of active parameters. Is that right?
Well, yeah. So I haven't even talked about the technique, but you're going to have a subset that's used, that's your active parameters, and you're going to have the total parameters. And so it's a little bit wasteful to say load up gazillions of parameters into my memory and then don't actually use them all.
Yeah.
Right. So if your only use case were for single users, you might want to just say, why don't I build a dense model that uses all gazillion?
Yeah. Yeah. Okay.
And that is probably the reason why Meta has not done MOE. I think we discussed that somewhere earlier, but a lot of the Meta's, Llama's use cases, 7 billion and 20 billion, whatever those models that people use in their personal systems. And
exactly. And to date, Meta's not in the business of serving you models and you paying them to do so. So if they're building small models like Llama 3.2 that you run on your computer, yeah, mixture of experts isn't necessarily beneficial for that use case. Great example. Thanks, Dave. Okay, so I'm going to go through this wonderful blog that I found, but I did want to just emphasize this idea. Even though I haven't explained the idea of mixture of experts very well yet, if you think about LLM layers, individual layers, layer 2, layer 6, layer 17, what is happening at that layer? It's doing things like find nouns, find verbs. Is this word the current word plural? Pulling up a fact, who designed the Eiffel Tower? Knowing that Bunker Hill can refer to a physical geographical place, but it also can refer to a famous battle from the Revolutionary War. Okay, so if you think that that's the kind of thing that a layer is doing, then you won't be surprised when the idea of an expert is not somebody that knows biology, somebody knows that French, somebody that knows math. Okay, but it's more like, I tend to process lots of digits and numbers. I tend to process lots of verbs. I tend to process lots of things, and not exclusively, but a lot of punctuation goes my way. So commas and periods and dashes tend to get assigned to me. Okay, so I just say this because, like, very much when I first heard the term mixture of experts, and many people I know, when you first hear the term, you think like, oh, so one's an expert in math, one's an expert in French, and that's not how it works. All right, so I'm going to flip over to my browser because this guy, Martin Grutendorst, I hope I'm pronouncing his name right. So he recently published a book with Jay Alamar, famously of the, illustrated transformer, illustrated BERT, illustrated whatever blog posts. And so it's a very nice blog that has lots of pictures. So here's the blog, and he explains mixture of experts. Not going to go through all of it, but the basic part of it, I think, is pretty good. All right. So yeah, there's their book. So what is mixture of experts? The two things that define, again, we're just talking about mixture experts used in LLMs. There have been many other kinds historically. So in this kind, what you need is you need to have a router that decides which subcomponents I'm going to go to. And then you're going to have subcomponents that we call experts. So you can imagine in a 60-layer DeepSeek model, each layer is going to have multiple experts. Here, we're showing 4, but it could be 8. In the case of DeepSeek, it's actually over 100. All right. And so what happens is each layer has a router, and it decides, let's say here, you're only using one expert. So on layer 1, I'm just going to use expert 1. On layer 2, I'm going to use expert 3, and so on and so forth, going through the different experts in the different layers. So if you recall the transformer architecture, is there a question?
Yeah, quick question. That one picture up. I assume that there is a router at each point here. Like it doesn't.
There is, yes.
Yeah,
this router is.
Yeah, every layer has a router.
Yeah. This is very conceptual, but actually the routers live right there next to the experts on each layer.
Yeah.
On the routers, is it a single connection like that, or does it go to like expert?
We'll see in a second. There's another better diagram. Yeah.
Oh, okay. Thank you.
So just a reminder that things like Llama, DeepSeek, GPT-3, these are decoder only transformer models, And so their layers have an attention layer that's decoder only, and then they have a feed forward or MLP layer. This purple feed forward layer is the part that we're modifying when we do mixture of experts. We're not changing attention currently. There's some people who've tried to propose some kind of variable pathway attention changes, but today we're just talking about the feed forward network part.
Okay. Hi, Ted. Are you sharing your screen yet? Sorry, I'm not seeing it.
Oh my goodness, am I?
No, we're seeing it.
We're seeing it.
Check to see if your Zoom window got covered up by something else. All right. So what does the feed forward layer look like in a vanilla, not mixture of experts model? Basically, you have your inputs, and then it expands it historically 4 times, these days 3.5 times, and then it shrinks it back down. And so this is just 2 fully connected layers, and there is a activation function that happens in the middle there. So this is just a very big, fully connected thing. If your LLM is relatively small, the dimension might be 512. These days, they're in the thousands, okay? And so going up would be up to 2,000 and then back to 512. And you can see here there's a lot of connections, right? So 512 times 2,000, there's a million different connections. There's a million weights here. What's a different way that we could utilize these million weights? So what we're going to do is we're going to split up these million weights. Let's say here again in the diagram,
Hey,
4
Ted,
ways.
May I interrupt just one? Sorry about that.
Yeah,
so
please.
Just want to clarify that 512 is the dimensions of each token. So it's not the sequence, it's the individual token that we run MLP on. And just to clarify for myself and for everyone.
Yes, so I'm talking about a model where every token is 512 floats. It's a vector of length 512. And so when we're processing that in the MLP layers, in the fully connected layers, what we do is we have just regular old linear fully connected neural network, and it goes to a higher dimension. And so there's like I said, for these days 512 was relatively small for an LLM. We would have 1 million weights in the first half and 1 million weights in the second half. It's pretty large. So the MLPs actually have more weights than the attention layers. They have 2/3 of the weights of a neural network, and attention only has 1/3 of the weights in a typical LLM. And so there's a lot of weights here, and this is how a really large model, like a 200, 600 billion parameter model, can actually know random facts like how tall is the Eiffel Tower? What year was it built? Who was the architect? If you didn't have billions of these, you couldn't encode billions of facts like that. And it knows this about the Eiffel Tower. It knows it about, the Space Needle. It knows it about, all of these like different things. It just knows lots and lots and lots of facts.
Hey, Ted, is there anything magic about that 4x size delta there or parameter?
No, it's one of those things where, right, when somebody builds a model that works, then it tends to become
the de
this
facto
rule of
standard
that everybody follows. So people followed that from 2017 until I would say about 2 years ago. So for about 5-6 years, people just followed this 4. Then somebody actually did some experiments, and they realized 4 was a little overkill, but it was very good. And so now a lot of the newer models use 3.5, which is not that different, but they found that they can get good performance. And so then that means that the feed forward, instead of being exactly 2/3 of the parameter of the non-embedding parameters of a model, they're now closer to 60% or something like that. So they're a little bit less. So attention is a little bit more powerful, so to speak, relatively, and the feed forward is a little less powerful relatively.
Got it.
All right, so let's just chop this up. So if we did 4 experts, then instead of 1 million parameters, we would have only 250,000 parameters in each of these 4 experts. And you can imagine, in my very made up example, if you had a sentence, the architect of the Eiffel Tower was named, probably of these million parameters, you don't need all of them. There's only a handful of them that somewhere encode the name of the guy that built the Eiffel Tower. I don't remember who it was. But so you can imagine you don't need all million of them, and certainly 1/4 is probably way more than enough if that's what your job was. In layer 12, your job was to, pull out the name of the guy who built it. 1/4 of the weights is more than enough. The trick, though, is that you need to make sure you send it to the right quarter, right? This router needs to actually do the right thing. And so that's one big question is how do you build these routers? How are you gonna know the right quarter to send it to? And so here you can see, kind of like I was saying, what are the things that when they just look at which token, which words inputs get sent to various routers, you'll see that maybe one of them gets in a page of text. This one expert got all the commas and the dashes and the parentheses, and this one got a whole bunch of times, and this one got a bunch of verbs falling identified, blah blah blah, right? So you do see some trends, but again, it's not like one of them knows math or something like that.
Hey, Ted.
Yes.
Is there any insight as to what would drive it towards that type of specialization? Like, I don't know why counting numbers, or what was the other ones you had there, that visual descriptions, what would make it move that logic to one particular expert?
So again, if we knew exactly how LLMs worked, how transformers worked, then we would know all the tasks. But if you think that a task for this layer is find an adjective that comes immediately before the noun because this is English, or immediately after the noun because this is Spanish, right? Then you would imagine that things like nouns and adjectives would be a great way to divide things up amongst the workers, because then those tasks are really well suited to it, right? And if you are an expert that just has memorized architects, then you probably want to be sent proper nouns or something like that. So that's the kind of thing, is that for me, if you think that those are the kinds of tasks, then this kind of division makes sense. Is this word the first word of a sentence? Is this word the first word of a clause? If that's your job to try to decide that, then like punctuation might be a really strong hint as to whether or not you're the first or last word, in a clause, something like that.
Yeah.
All right, so here's another example. This is this is code, and so the different colors show which expert it went to. And so you can see that, for example, the word module appears multiple times, and each time it goes to the pink expert. And then certain words went to the blue one, certain words went to the green one. If you look here, you can see like the double underscore here went to one expert, and the double underscore there went to a different expert. So it's not even, super very literal about syntax. I don't think they've said in here from the Mixtral paper which layer this is. I assume this is not the very first layer. The very first layer, the experts are probably very grammatically, syntactically, right? But once you get to like layer 15, you've now encoded a lot of information, not just what this token is, but what came before it. Where you are in a sentence, or where you are in in this case, code, like where you are in a line of code.
In this one, it almost looks like it's figuring out contextually. Let's take list, the word list there, right? It's used as like a modifier for module list or something like that. And the other one, it's used as an, what we would call an object in coding, right? I don't know what you would call it in this particular one. It's almost looking like it's figured out sort of usage, if you will.
Yeah.
Is this a
Right.
separate conceptual object, or is this just some sort of characters on as a modifier here?
That's right. So that's what I'm saying is that by the time you get to layer 17, it knows not only the word list, but that this appears at the beginning of an expression or whatever, and it knows that this is part of an identifier that it's just and so it makes sense that it could process these differently when it's
Right.
just part of a function or other identifier you've created versus this is the beginning of an expression. Yep.
That's pretty impressive,
Yep.
learning, if you will. That's pretty subtle,
Yep.
if you will.
And to me, it's not surprising that in code you would see things like parentheses and square brackets and dots and commas, that those all get kind of processed specially because they do have very much more meaning than in English language, right? In code, they have like really, really specific meaning. So it kind of makes sense that maybe there's experts that, and not necessarily the same expert, but there are experts that specialize in dots and parentheses.
But interestingly, if you look at the dots, like there in n dot on the second line, you have n dot module, and that's on the purple expert, and on the fifth line, you have nn dot module list, and it's on another expert.
Yes. So that's why I'm saying, if you have a mental intuition, a mental model for experts, don't think of them super literally. Okay?
Yeah.
They're doing these
Obviously.
complex tasks. And what I said in the slide is I process a lot of tokens, many of which are verbs. That doesn't mean that you only exclusively get verbs and that verbs never go to another expert, right?
Mm-hmm.
So think of it a little bit more broadly. And gosh, if we knew exactly what the LLM was doing, we probably could figure out exactly why the dot went to one expert and a different, you know what I mean? But because we don't really know all the details, it's hard.
It's just amazing that
Okay.
it does work that well.
Yeah. Okay. So what I'm trying to get to, so you can see, by the way, in some of these diagrams that if you have three experts, the token, MOE does not necessarily have to go to the same expert in each layer, right? Every layer is deciding separately how it's going to do things. And somewhere finally we get to, here's what the router actually is. It's actually just a really, really tiny linear layer and then a softmax. So we saw before we had 512, right? If your tokens are length 512, you have 512 floats, you run it through this tiny little linear thing, and it's just going to have like 512 weights, right? At the end of it, you get a logit, and you run that logit through a softmax. And so then you might have, for however many experts you have, if you have 4 experts, you're going to have 4 numbers, and they're all going to add up to 1. Okay. So one strategy for MOE might be you say, I'm going to use 1 expert out of my 4 for every token. And so then you take the biggest number, 0.45, and that's where you send your token. Another strategy might be you say, I'm going to use 2 of 4. And so then you take the top 2, the 0.45 and the 0.31, and you use 2 out of every 4. So you really, as the designer, can choose how many out of how many.
Okay. Ted, is this a greedy selection algorithm, or is there's some stochastic kind of sampling that goes on at this layer?
So that's an issue that we're going to run into next. Yeah. Okay. So by default, it's just a straight deterministic algorithm, and if every single token got a 0.45 for expert 1, then at this layer you would route every single token to expert 1, and you would never use experts 2, 3, or 4.
Okay.
Okay. And then I think that's the basic gist of what's covered in this blog. It then goes and talks about a little bit of the math. You know, you're doing a soft max, blah blah blah, and it talks about some different famous models like T5 or whatever that use a mixture of experts. But so yes, so going back to the slides, we have this issue about routing and resource utilization. Okay, so because the tokens in each layer, they get routed to a subset. So famous model from the past, approximately a year ago, Mixtral was a 2 of 8 model. So it had 8 experts, and every layer would use 2 of those 8 experts for each token. Okay. So because they're routed to a subset of the experts, the number of parameters used to process a particular token is a lot less than the total number of parameters you have. So in the case of Mixtral, it's 1/4 of the weights in your model are used on the MLP layers. Now you're also using 100% of the weights in the attention layers, and so you have to like kind of blah 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 blah. And so that's where you'll see something where they'll say Mixtral had 70 million parameters, but only 30 million of them are used to process each token. That's the math that you do to sort of figure this out. And again, as I kind of alluded to earlier, if you have a server with many users, then maybe this token was assigned to experts in this layer, was assigned to experts 1 and 2. But a different user has a different prompt that they're completing. And so it got assigned to experts 3 and 4. And somebody else got assigned to 5 and 6. Somebody else got assigned to 7 and 8. And then if you have lots and lots of users, somebody else got assigned to 1 and 5, and somebody else got assigned to 2 and 8, and somebody else got assigned, right? But on average, what's going to happen is if you do 2 of 8, each expert will get used 1/4 of the time, ideally, okay? And so then what you do is you can say that I don't actually need enough GPU horsepower for every expert to be able to process. If I have 100 users, I don't need them all to be able to process 100 users. Each expert GPU only needs enough horsepower to process about 25 users because they're only getting used on average 1/4 of the time. So the attention part of your computer network needs to be beefy enough to process 100 users because it's always getting used. But the experts, you can actually design your system so that you size it so the expert part only needs to be beefy enough to handle 25 users in that same amount of time that the attention is handling 100 users. So for a server type situation, which is what DeepSeek is doing today, they haven't historically done a lot of it, but they got a lot of good press. So they have a lot of people, sending texts through the system, OpenAI, doing that, Claude's, right, Sonnet. And as Dave was pointing to earlier, so things like Llama 3, that's not really the way most people use Llama 3. The way most people use it is they download it and they're running it on like 1 GPU. And so then this is not something that you can do. You're not really averaging the load across many users. But for that server use case, for the really ginormous models, this actually is a pretty good fit. Okay. You do, however, even though your compute is sized for what I totally made up numbers, 30 billion parameters out of 70 for Mixtral, right? Even though your compute is 30 billion, you need enough memory to hold all 70 billion. So that's a potential downside. Again, on the server side, you don't really care because you have got so many users and you're averaging things out. But for an individual person, and so this way of spreading the load across for different experts across different devices, this is what they call expert parallelism. So you hear about data parallelism and tensor parallelism. So expert parallelism is where you just say, yes, if you're using the simple one is 2 of 8, you only need 25% capacity. So it turns out that there are lots of complexities that arise when you're trying to do this expert business. And I don't have a lot of slides on it. I didn't find a lot of resources, but basically one of the things is when you're training, you want all of your experts to get used equally. You don't want all of it to go to expert one and none of it to go to the other experts, okay? But it turns out that there's this problem that when you're training, we start with random initialization. So let's say initially randomly, expert one is getting a lot more of the tokens than the other experts. That means that when we do backpropagation is updating the weights on expert one more than the others. So actually what happens then is expert one is actually better at doing whatever it does than experts 2, 3, and 4. And so if you had a strategy that basically said, like, ideally, I'd like to route my tokens to the expert that will reduce loss the most, that will process it the most, that will do the best job of next token prediction, you actually get into a vicious cycle where the ones that lucked out and got a little bit more training continue to beat out the ones that got a little bit less training. I don't know if you guys heard about that famous study that showed that professional hockey players all had very similar birthdays because there was a cutoff date for youth hockey leagues. And if you were just after that cutoff date, then you were 11 months younger than the people who were just before that cutoff date. And so what happened is kids who had these birthdays who were on average 6 months older than everybody else, and in some cases 11 months older than the people who were on the other side of the cutoff date, they did better in Pee-wee hockey. And then they were still 6 months older and they got more playing time in Pee-wee hockey. So now they had a double advantage when they got to youth hockey. And then they were still 6 months older and they had even more playing time. So they had an advantage in junior hockey. And so then by the time you get to the NHL, you're like, why is it that all these people have birthdays in, like, I don't remember what the cutoff was, but like May and June. And there's almost nobody with a birthday in July and August. And it's just because of that thing. So that same phenomenon happens here where there's this self-reinforcing cycle. Thank you in the chat for the reference. Yeah. So fascinating thing. Recommend people read up about that. And so the same thing would happen here. So basically what you want to do is you want to have some mechanism that hard forces the experts to be spread evenly. And I'm not going to go into all the details about how that happens, but that's one of the things that you need to do. So DeepSeek, they said, we're going to use mix for experts, but we're actually going to use it very aggressively. We're not going to have 8 experts. We're going to have it very fine-grained. We're going to have hundreds of experts. So then that means that you might not have an expert that gets all verbs because you don't have 8 of them. You've got hundreds, right? So then maybe you have an expert that instead of getting all verbs or, like a lot of verbs, it might only get a certain fraction of action verbs or whatever, because it's much, much, much more spread out. The other thing that yeah.
Ted, is it the right intuition then these will actually, because there's so many of them, they'll become more focused specialists?
Yes.
Yes,
right? They're more fine-grained, more specialized. But it turns out that there are functions that these MLPs do that are very heavily utilized. And so what the DeepSeek team apparently experimented and found was that it's very difficult to get, once you increase the number of experts very large, it's very difficult to get even utilization over 100 different experts because there's some things that just need to be done over and over and over and over again. And so what ended up happening is if you force it to spread it out, then it just makes copies of expert 1. So expert 2 does the exact same thing as expert 1, and expert 3 does the exact same thing as expert 1, because you're just forcing it to spread it out, okay? So the switch that they made here is this second bullet, is they said, let's have a small number of experts that are always on. They're not part of the routing mechanism. Okay. So if I've got 200 experts, I'm going to have 4 that can be like, one of them can be like, what do I do when I see a period? What do I do when I see a space or something like that, which just comes up all the freaking time. You don't need to worry about wasting parameters, just having multiple experts that you've forced to spread this out to do the same thing over and over again. So I'm sure they did some experiments, and basically what they found is that, I think it was something like 4 experts is enough to handle every single token has a shot to have these tokens, these experts weigh in on what to do. And then the other 100 and whatever, 50, how many that, 256, those get spread evenly amongst all these fine-grained experts. It's not easy. I'm sure a lot of engineering went into how do you come up with this scheme? How do you get to spread very evenly over those 250 experts and all that kind of stuff?
So that's not anything they documented then?
No, they said they did it, but like the entire recipe is not there. And so that's where I saw one person very carefully said, DeepSeek V3, DeepSeek R1 are open weight models. We have the final model. It's not an open source model because we do not have the source code that was used to train it. We don't have all the details.
Right, right.
They recently released that Deep EP, which I haven't read through it, but that may allegedly goes into the deep, into the expert parallel.
Yeah,
what
they are
is
releasing.
That, Roger?
They're releasing more and
Deep
more pieces. EP is like expert prediction or something like that, or
yeah, I don't expert.
but anyway,
So
they are releasing
they
more. What was that, Dave?
Oh, just saying the same thing you're saying, actually, Ted. This week, they haven't, every single day, they've called it the open source week. So they have been releasing the key modules that we've been discussing for the last 3-4 weeks, one every day.
Oh, okay. Yeah. So their job as a smaller company, they're not the OpenAI. Their job is to get as much publicity as possible. Okay. And so they're going to do these kind of tactics. But just as a side comment, there is a difference between open weights, which means you can use the model, and open source, like many other projects in general on GitHub are open source, where you have fully 100% everything reproducible, everything, kind of to a certain extent.
And just a little caveat with open license is important to read for any open thing.
Yes. Okay. So one of the big innovations they had that I don't think I've seen anywhere else that they really did was to say we're going to have shared experts that are always used, in addition to this aggressive, very high number of experts. Then the next thing they said is, when we've finished training this model and we're going to run inference, if we're going to have millions of users, what's going to happen is, let's say, I don't remember but if they did something like 8 of 250, okay, then the whole thing I said earlier about, like, on average, as long as each expert gets used equally, 1/250th of the time, right? Then like, the load on all the experts will average out just fine. But there's another caveat that if you have 8 experts and they're physically on 8 different devices, then once those experts have run, you need to communicate to combine all of their outputs together, along with the 4 always use experts. So wouldn't it be really nice if those 8 experts happened to all be on the same device, or if they can't fit on only 2 devices instead of on 8 different devices? So in addition to saying that we want each expert to be used 1/250th or 8/256th of the time, they also, in DeepSeek V2, added a term to the loss function, which basically says, how many devices did these experts live on? And they penalize you for the larger that number is. Okay. And they penalize you for the communication that has to happen between those devices. So these 2 extra loss terms. And basically what that means is, then you might originally have had an expert that gets all the commas and an expert that gets the action verbs, let's say. Now you can decide, should those two functions live on device 1 and device 4, or should those two functions be the experts that actually share a device? So that's the extra wrinkle that they did. And so then in DeepSeek v3, they said, we still want to do this, but instead of using a loss function, what they did is external to the model. So this is not part of the loss function. This is not part of the weights. As the thing is training, they just had a separate piece of code that monitored how much each expert was being utilized. And they would basically then modify the routing algorithm with this bias term. So if something wasn't getting used enough, then they would add a positive number to make it more likely to be used. And if it was used too much, then they would use a negative number, and they would do it this way. And I don't know, maybe that's part of the Deep EP that they released is how they do all of this stuff. But basically, they're using a second external program to nudge the expert choices around rather than just using the loss function. And so in the DeepSeek v3 paper, it says that they found that worked better than trying to use the loss function. And you can imagine you don't really want to contaminate your loss function, your next token prediction, too much by this expert business. So if you can just handle it separately, then why not? All right, so definitely didn't get into all the gory details about each of these steps, but to kind of wrap things up. So these MOE architectures, they're used just at the MOP layers. They do, apparently, according to DeepSeek and other people, speed up the training. They reduce, on a certain level, your compute cost during inference, because let's say you had a model that has 70 billion total parameters, but you only use 30 of them at once on any given inference. What people find is that the score you get on benchmarks and other things is sort of similar to the 70 billion dense models. Okay, so that's why I say like reducing compute cost, because you get just as good performance as if you had 70 billion dense, but you're actually only using 30 billion at a time or something like that. Yeah, Shuling, your question?
Hi, Ted. Yeah, I just have one question actually about the experts. How do they make sure that one expert focus on one thing, like one expert focus on commerce and the other experts may focus on the how do they achieve that?
Yeah, they don't. Basically, what they do is they have the router send certain tokens to experts. So basically, if you're the expert that gets all the commas, then you need to decide what to do when you get commas. And if, in general, LLMs learn to do certain patterns with commas, right, then that's the expert that's going to learn what to do because it always gets the commas. So in a perfect world, what would happen is your router would learn very early which experts to send things to. You don't want the router to be changing things up late in training. You'd like your router to get set early. I don't know if that's the case or not, but intuitively, that's what you would want.
Got it. Thank you, Ted.
Yeah, thanks for the question. Yeah, Patrick.
No, it's Patrick's got a question.
Howdy. I'm curious, Ted, this sort of hardware-aware loss-based optimization, have you heard any other examples of that? This is, for me, the first.
No, actually, I didn't. I don't know that I emphasized this point well enough. So when you have this loss function or this external thing that's saying, I'm going to calculate a loss whether you're on the same device or not, in order to implement that, you need to know in advance exactly what hardware you're going to be running this on. So for DeepSeek, this was kind of like, yeah, we know we only have these kinds of GPUs, so we're planning to run this on our H800s, and so we're going to have this many experts. They're going to be spread this many experts per GPU, and therefore we know how many devices they're going to be and all that. So yeah, it is somewhat of a limitation because you couldn't just generically take their DeepSeek model and run it on an arbitrary set of GPUs that you leased from Amazon, from AWS or whatever, you know what I mean? So yeah, I'm not aware of anybody else that has done this, and it does kind of box you into a corner.
Do you know if this made a big splash, this aspect of the training? Because to me, it seems extremely novel.
I don't know. I don't know. I mean, it's definitely one of, you know, they threw a lot of clever little engineering tweaks here and there, and this is one of them. And it just happens to be that this trick works better for them with their GPUs than if somebody else. You know, most people are talking about like using the smaller versions of the model that they fine tune, like to fine tune whatever, Llama and Quen, whatever. Most people are not actually using the 600 billion version. If they are using that, they're just going to the DeepSeek website and running it there. They're not downloading the weights because that's just huge, right? So, but it does mean that like if Perplexity is actually using DeepSeek R1 or something like that, then they have a certain amount of work they need to do to try and get their hardware to match the way this model was specifically tuned.
Right, right. Cool.
Yeah.
Thank you.
Yeah. But I think, you know, most everyday people are not. So then they're not running into the issue that it's designed for you to assign things in a particular way. Yeah. So just for the sake of time, gonna keep going here. So mixture of experts increases the total amount of memory needed in one sense. So it's not really helpful, like I said, for running on a single GPU, but for big companies who are doing serving, then they can balance multiple users and use this expert parallelism. So DeepSeek used MOE, used a very large number of experts. Off the top of my head, I don't know anybody else that's used 250 experts. It was in V2. They kept it in V3, but they did tweak the strategy a little bit of how they both get experts to be evenly used and as well as which physical experts get used together so that they can increase the fraction of the time that they're on the same device. And so then they don't need as much communication in order to combine the results, sum up the results. And then I'll PDF this and I'll share this, but this was the blog that I was looking at, and these are the DeepSeek papers that we've been talking about.
So Ted,
all right, and
I did kind of, I'm sorry, were you done there?
Yeah, I was just going to say, any other general questions about MOE?
So, yeah, a thought occurred to me as you were going through there that kind of an intuition around how it is more efficient, where dealing with something like a comma or something like that seems like a simple concept. If I can think of it as kind of the compute that goes into it, the number of parameters goes into it, it seems like that type of token is a lot easier to deal with than some of the others. And so it feels like, yeah, you know, why have an MLP with 2048 in the intermediate layer when you could do it with, you know, 64 or something like that? It feels more efficient. I don't know if that's the right intuition, but it makes me wonder if anybody has ever explored very varied sizes of experts. In other words, if you divide it up to where you have smaller chunks for certain functionality and larger chunks for more complicated concepts.
I'm not aware. I think that DeepSeek is really the first I've seen a paper where people went for a very large number of experts. Mm-hmm. One other thing that I've seen is that if you look at the I'm pretty sure that the conventional wisdom is that when an MLP in layer 17 gets the input token and then its output gets added to the residual stream, right?
Right.
Okay. That the the activation of that MLP is very sparse. The thing I remember distinctly is that if you look at the average magnitude of the vector that it's outputting that's getting added to the residual stream, the average magnitude is relatively low.
Okay.
Okay. And I think that's consistent with a relatively sparse activation. So what you can imagine is that in a dense non-MOE architecture, it's possible that if you think of this matrix multiply, right, as just basically like being a whole lot of columns that you then take the input vector and you dot them against.
Right.
Okay. If you use that intuition and you say that basically what's happening is that the input vector is orthogonal to almost all the columns.
Mm-hmm.
Okay. And so somewhere here, there's an Eiffel Tower column that's like, oh, you're actually talking about the Eiffel Tower? Bing! I'm going to output something. But any other token that comes in, if it's the George Washington Bridge, if it's Montana, if it's Atlantic Ocean, then it just outputs zeros. That particular column of the matrix,
Yeah.
right?
Yeah.
So if you think about it that way, then if the router knew which columns were going to be non-zero, it could be 100% just as good.
Yeah.
But only route it to that tiny fraction. The question, though, is can your router actually know that well enough?
Right.
And the way I think of it, I don't know, I haven't read this anywhere, but the way I think of it is not really that the router knows, but rather what I was saying to earlier is that if the router can get frozen relatively early, then the Eiffel Tower will get routed to this expert.
Yeah.
And if it's going to learn anything, it needs to learn the things it needs to learn in order to function as an LLM for the Eiffel Tower.
Yeah.
So I think of it as the other way around. Not that the router is really smart, but that the router gets...
It teaches different experts.
Yeah, it basically says you are going to be the expert on the Eiffel Tower and you're going to be the expert on commas because that's what I'm sending you.
Right. No, that makes sense. That makes sense.
It also whether you like it or not.
It occurred to me that based on some of our other talks, like the Rome talk and whatnot, that information is kind of distributed through the MLPs. It's not like in one MLP, it's in multiple layers. So a router that gets it wrong doesn't mess it up. It gets another shot at it. Another router is going to get another shot at it.
Yeah, and there were even early routing strategies that would say things like, we didn't train this super well. Well, actually, maybe we trained it to get it close to 25% on, let's say you have 4 experts, 25% of each expert on our training distribution. But then you give it a particular input, like, please solve this math word problem. Sally has 8 apples and Sally does this and that. And somehow, just because of the words that you chose, expert 1 is now getting 50% of them instead of a quarter.
Yeah.
Okay. Early MOE stuff would just simply say, once you're past the GPU utilization that expert 1 can handle, let's say it's 30%, we just drop everything else on the floor. And again, because things are distributed, it didn't tend to catastrophically break things or whatever. And then people said, let's build a little whatever. And so then it's like, okay, we couldn't send it to expert 1, so we'll send it to the expert that had the second highest score.
Yeah. Okay.
Instead of dropping it on the floor. And so there have been some strategies like that. But as far as I can tell, like with just a very small amount of experimentation, okay, you could design an input that will always get routed to the same expert.
Yeah.
So maybe if your input was just comma, right? Maybe that'll do it. Maybe not. But with just a small amount of work, assuming you have access to the internals, you could quickly tweak your input to make it always hit the same expert so that it does not average out at all. And so at the end of the day, there always is, at inference time, a fail-safe plan where if an expert gets too much, it'll offload it or just drop it on the floor. Right? No matter how you've trained it, somebody can design an adversarial input that always uses the same experts.
Right.
So yes, that still comes up where no matter what you've done in training, you still have to have the contingency plan that says, once I hit my max GPU capability, I'm out. And the good news is that doesn't seem to completely break things.
Does this imply that this is tied then to what your data center looks like? I mean, how many machines you have and things like that?
Well, in general, like Mixtral 2 of 8, it's not really tied to machines, whatever. And then the DeepSeek stuff, you're going to get better performance if you kind of match their architecture, because they tried to cluster which experts fire
right,
together.
Exactly. Yeah.
Because it'll work correctly. You'll get correct results on any assignment of experts. But if you cluster them the same way they did, then you'll actually see less communication. You'll get higher throughput.
But I'm just wondering from their perspective, if they were training it, and let's say one machine takes a dive, right? Is this like start over again, or?
For training, you said?
Yeah. If you were doing your initial training run or something like that.
The more I've read,
there's fragility here.
It's a little bit like if you remember, like RAID for disks.
Oh yeah.
Right. So you get this great parallelism and speed up, but the more you do this, the higher the odds of a failure somewhere. And so yes, actually being able to checkpoint and or recompute stuff. And so so I think the Llama 3 Herd of Models paper talked a little bit about that they actually had infrastructure that would allow them to basically take a delay in time where it's like, oh shoot, node 3 went down. Now I need to send the computation that was going to go to node 3 to node 4 and have it redo those calculations. And we're all going to sit around waiting for node 4 until it finishes.
Gotcha. It has to catch up essentially and get
so you lose in terms of a delay, but you don't just get fatal error, crash. Now I need to start over at a certain checkpoint.
Okay.
Right. Yeah, so you're willing to like have that one batch take way longer than it should have, rather than having to go back to whenever. If you only checkpoint every hour, every 12 hours, you don't want to have to go back to the last checkpoint.
Right. Okay. I see what you're doing it. Thanks.
I'm just reading elsewhere in the paper where it's saying during inference time, they'll actually monitor for overloaded experts and bring up redundant experts to cover for that.
Oh, like extra hardware.
Or I didn't determine whether it was extra hardware, like extra nodes, or just like an extra copy of a particular expert sitting on the machine. So but the idea is dynamically balancing, adapting to the load.
Yeah, that's another negative I didn't put that maybe I should have added. When you use MOE, it does require this inference time monitoring of expert utilization.
Right. Yeah, because even at runtime, when you're using it, if one node craps out, you have to adjust accordingly.
Well, if a node crashes at runtime, I think they just redo the whole thing. But it's not training where you're really losing a really long, I get yes, I'm saying if you had either because of an adversary or just bad luck, if you had a whole lot of stuff going to expert number 1, then typically, rather than having your inference rate drop, right? So in Mixtral, you're only supposed to get a quarter. So your inference rate would drop to 1/4 of what it should be if you were letting all of the expert work go to expert 1.
Right.
Instead of doing that, what they do is they cap how much can go to expert 1 to keep up their inference rate, but to lower the quality of the inference by either sending it to a different expert or just throwing it on the floor. And that's this extra software that you need that's monitoring your expert loads. So that's another downside.
Hey, Ted, so if we compare this with the regular non-MOE MLP layer, I'm assuming for a model size like DeepSeek V3, each MLP layer possibly does not fit on a single GPU, or does it? I'm assuming it doesn't.
Absolutely not. So they're spreading the experts across many, many GPUs, and that's where that expert parallelism comes in.
But
right,
each
right. But
expert is on one GPU.
No, which is fine. Each expert is one GPU or maybe two GPU or whatever. But if an expert cannot be on a GPU, then of course the entire MLP layer cannot be on the GPU anyway to begin with. So the question that I have is that the routing for the is there any engineering work around how the routing or the distribution of weights for which would be basically in that case the model parallelism for MLP layer, because we could potentially run into those issues. Well, there is always communication there to begin with, and it can be communication across InfiniBand or within the node, or those kind of trade-offs that one has to look at. And I'm just wondering, like, in some sense, it's somewhat related, not fully related, but can some of those learnings be brought over here that, hey, if I'm talking about a single layer experts, that I always want to limit it how I limit it for a single layer's MLP without MOE.
Yes, so I saw a comment somewhere, I don't remember where, and I'm not sure, I didn't say something in the presentation because I'm not sure if I fully understand it. But basically, my understanding of the way this gets implemented at sort of like the CUDA at the GPU level, okay, is let's say you were handling 100 users and a quarter of them are supposed to go to each expert. Then basically that would be 25 on average, but you allow for some ups and downs or whatever. And so you actually hard code in your capacity factor for each expert. And so basically what you say is, I'm going to send 30 things to expert, up to 30 things to expert 1, 30 to 2, 30 to 3, 30 to 4. And then when the workload comes in, you basically have a predefined buffer that's 30 long that you fill up. And so once you get that 31st user, it is not going into the buffer that's getting assigned to expert number 1. Okay. And that's how this expert overflow thing gets handled, is that I don't really know technically if it's CUDA or the layer below CUDA or whatever, but that basically you have somewhat of a fixed computation graph. And so you're really saying, like, my computation graph is 30. That's all that each expert can handle. That capacity is hard-coded in there. And once you fill up that buffer, it goes off to the expert, and then nobody else gets to use that expert. Does that make sense, what I just said?
Yes. I was also trying to compare it to the non-MOE allocation of GPUs, MLP allocation in the non-MOE case, and any learnings from that side. But I understand, because you could potentially distribute your weights for MLP in a non-MOE, the regular, the vanilla Llama style MLP.
I think anything you did with sort of with layers and parallelism there, and anything you did with data parallelism, whatever worked with a single giant MLP, you now can certainly do the same thing with MOE. It's just that whatever physically was assigned to one MLP, now you spread it out with multiple experts. And theoretically, what it means is it should work better because you have less communication, right? When you have a giant MLP, all the results need to ultimately get combined, because everybody talks to everybody in a layer, right? And in this case, each expert gets to kind of be on its own, and they don't have to talk to the other experts. So MOE does reduce the bandwidth of communication you need in the MLP. And so to the extent that your MLP didn't fit on one GPU, let's say it took 4 GPUs to have enough RAM for it, right? If you have 4 experts, that's actually kind of really helped your problem a lot, because now instead of the 4 always needing to talk to each other, you know, they combine outputs, but not in the middle. Does that make sense?
Yeah.
So I think it's there's that extra bookkeeping overhead, but otherwise I think it's like universally better for parallelism if you have MOE.
Okay.
Okay, nice job.
Yeah, thank you.
Thank you. Thank you, both of you.
Yeah.